Hello everyone, and welcome to the online lecture for college algebra. In this video, we're going to cover section 2.4 on operations with functions. In total, we're going to be looking at 5 different ways that we can combine functions together in this section, the first 4 of which are called the basic operations. And these are combining the operations together with our traditional operations, addition, subtraction, multiplication, and division. And these 4 are pretty straightforward. So for two functions, we'll call them f and g, just to give them names, with domains that I'm going to call d of f and d of g respectively. Then if you want to define the function f plus g of x, all you do is add the individual functions together. It's going to be f of x plus g of x, and its domain is the intersection between the two individual domains, domain of f and domain of g. Now, recall from the video on solving inequalities, the intersection is the overlap between the two domains. So it is the x values that are in both, essentially, which makes sense because if you want this thing to be defined, f plus g of x, you need f of x to work, so x has to be in the domain of f, and you also need g of x to work, so x also needs to be in the domain of g. So the domain of the combination are the x values that are in the domains of both f and g at the same time. Another way to think about it is it's combining the restrictions of both domains together as well. Because any restrictions on f, anything not in its domain, won't be in the domain of the combination, and any restrictions for g also won't be in the domain of the combination. Now, even though I'm writing it as an intersection right now, domain of f intersected with domain of g, most of the time you can just look at the final function and figure out the domain from it, as long as you don't simplify first. Because sometimes once you start combining functions together and simplifying, you can lose restrictions. All right, so those are your options. You can find the domains of the functions individually and then look for where they overlap, or you can find the domain of the combination itself before you simplify. All right, so the next couple of operations are going to be pretty straightforward as well, especially now that we've gotten kind of the talk of the domain out of the way. For f minus g of x, that's just going to be f of x minus g of x, and it's going to have the exact same domain. It's the intersection between the domains of f and g, the x's that are in both. If you want f times g of x, that's just f of x times g of x, and it also has the same domain, the intersection of the two domains individually, f and g. And that leaves us with our final operation, which does have a bit of a twist to it we need to be careful about. F divided by g of x is still just f of x over g of x, so the format just tells you what to do with the two functions. And its domain is also the intersection between the two, but because you're introducing division, you get some additional restrictions potentially. You have to be careful that you are not now dividing by 0 as well. All right, so you'd start with the same domain that you had for the other three, look for the overlap between the two, but then you would also remove any values on top of that that would cause you to divide by 0. So just an extra step at the end. So let's take a look at some basic combinations and function evaluation that goes along with it. So in example 1, we are given 3 discrete functions, f, g, and h, as a list of ordered pairs. And for part A, we're asked to find f times h of 2. And we're not even asked to find the domain or anything like that here. So this is really straightforward. It's just straight up going by the definitions on the previous slide. So fh of 2, by definition, is just f of 2 times h of 2. And so now we just evaluate each of those functions individually. So f of 2 would be 0. H of 2 would be 4, but 0 times 4 is still 0. Similar for part B, we've got f minus g of negative 3. So by definition, this is just f of negative 3 minus g of negative 3. And again, we just evaluate and then subtract. So f of negative 3 would be 1. G of negative 3 would be 2. And so we get 1 minus 2, or a negative 1. Just like when we were evaluating regular functions, single functions, back in section 2.1, if you plug in a number, you get out a number. So let's go one step further than what we were doing in example 1. In example 1, we were evaluating the combinations at a point. So we were evaluating, say, g plus h of 1 or g plus h of 2. Now we're going to be asked to find the entire function, g plus h. So that means its final form is going to look a lot like the ones we're starting with up here. It will be a list of all ordered pairs that work for g plus h. And we're also asked to state their domain. Although the appropriate way to go about this is kind of in the reverse order. We're going to find the domain first so that we actually know what possibilities we have for inputs for g plus h. So this goes back to the definition. G plus h, I'm going to think of it in terms of x right now, is g of x plus h of x. So we're looking for the inputs that they share, the inputs that they have in common. Remember, the domain is the overlap between the two individual domains. So what x values or what inputs do g and h share? That's what we're looking for here. So g has inputs of negative 3, 1, 2, and 4. That's its domain. Whereas h has inputs of 2 and 1. That's its domain. So if we're looking for the stuff in common between the two, the overlap, negative 3 is out, 4 is out, because those are not in h, but they share a common input of 1, that'll work in both, and they share a common input of 2, that will work in both. So these are the ones that we can make work. G and h share 1 and 2. And so now what we want to do in order to fully define the function is just evaluate g plus h of both of these. These are our inputs. We need to figure out what the outputs are. So let's start with g plus h of 1. By definition, that's g of 1 plus h of 1. G of 1 is 2. H of 1 is 0. So this would be 2 plus 0, or 2. Now when I go to write this as an ordered pair in a second, I need input, output, x and y, essentially. So pay close attention to what's happening here. Our input is all the way over here on the left. What we plugged in is 1, and our output is all the way over here on the right. We had an output of 2. So as an ordered pair for the function g plus h, this would be the ordered pair input of 1, output of 2. That will be one of the ordered pairs when we define the function. All right, so we got one more number to try, that's 2. We need to figure out this one as well. So let's do g plus h of 2. That one is g of 2 plus h of 2. G of 2 is 6. H of 2 is 4. So we get 6 plus 4, or 10. So as an ordered pair, this had an input of 2 and an output of 10. So now we can fully define the function. G plus h, the function, written in the same format we have up here, it's a discrete function, a list of ordered pairs, is fully defined by 1, 2, and 2, 10. We still need to list out the domain as well. And we already found that in advance, but you can also read it from the x values of the ordered pairs here as well, just like back in section 2.1. The possible inputs here are 1 and 2. And again, only those two would work, because any other number you plug in would either not work in G, it wouldn't be part of G's domain, or it wouldn't work in H. It wouldn't be part of H's domain. You're looking for the stuff in common. So let's do one more. Part B, we've got G divided by F, and we want to fully define this function. So let's start by looking at what they share. What inputs would work in both? Well, we've got a -3 in common, so that's one that would work in both. F has an input of 0, but G doesn't. That's no good. They have a 2 in common, and G has an input of F, but F doesn't, so that's no good. And if you have trouble seeing what they have in common as a list of ordered pairs like this, you could always write out the domains. So if we have domain of F, that would be -3, 0, 2. The domain of G would be -3, 1, 2, 4. It's basically doing the same thing, but without the y values getting in the way. Look for what they share. This is technically an intersection between these two sets. All right, so we've got all of our possible inputs. There's only two again, -3 and 2. So now we just need to find what the associated outputs are. So let's start with G over F of -3. So by definition, that would be G of -3 divided by F of -3. G of -3 is 2. F of -3 is 1. And 2 divided by 1 is, of course, 2. So we've got input, output. This corresponds to an ordered pair of -3, 2. All right, so that's one down. We got one more to go. G divided by F of 2, by definition, would be G of 2 divided by F of 2. G of 2 is 6. F of 2 is 0. That's a problem, because dividing by 0 is undefined. This does not exist. So we don't get an ordered pair here. This failed. Right, so if this were something like G plus F, G minus F, or G times F, the domain would be -3, 2, because that's what they share. That's the intersection. But in this case, we also have to remove 2 from the equation. That's an additional restriction because it divided by 0. And so we only ended up with one ordered pair this time. Only one thing made it through both. The function G divided by F is just the single ordered pair -3, 2, which means the domain of G divided by F, possible inputs, is just the single number -3. So now let's take a look at some examples involving continuous functions, and the idea is the same, although it does require a little bit more complicated function evaluation now, and the domains, of course, will be a little bit trickier this time around. But no domains here in example 3. We're again just evaluating at a point, a number or a letter. So in part 1, we're asked to find G plus F of 3, where G is the function x squared minus x, and F is the function x minus 3. So by definition, G plus F of 3 is just G of 3 plus F of 3. So let's figure out what each of those is. For G of 3, we're going to plug 3 into G everywhere there's an x. So that would be 3 squared minus 3, which would be 9 minus 3, or 6. And then this is going to be plus f of 3. And that one's going to be a little bit easier. If you plug 3 in for f, you just get 3 minus 3, or 0. So this is 6 plus 0, or 6. Part 2, we've got f divided by g of b, so we're keeping it more abstract this time. By definition, this is just f of b divided by g of b. And now it's just function evaluation. So if f of x is x minus 3, f of b would be b minus 3. And if g of x is x squared minus x, g of b would be b squared minus b. And that's it. Don't try to set this equal to 0. Don't try to solve it for b or anything like that. Right? Just like before, when you plug a number in, you get a number out. When you start plugging letters in, you get a new function out. So in example 4, we'll once again go the route of fully defining these combinations. So this time around, we're asked to find an equation defining each function and state the domain. So we want to find the domain of the combinations. Well, let's do a little bit of prep work here. We can find the domain of each of these three functions, f, g, and h individually, relatively easy. So f is square root of x. So we need the inside of that square root to be greater than or equal to 0. So f's domain would be 0 to infinity, 0 included, because square root of 0 is fine. G of x is the line x minus 4. No x's in square roots, no x's in denominators. This one has the domain of all real numbers. And h of x is the rational function 1 over x minus 2. And so we don't want to divide by 0. That happens when x is positive 2. So this one's domain is all real numbers except 2. Which in interval notation would be negative infinity to 2 with parentheses, unioned with 2 to positive infinity. Right? But it's also worth just thinking about this as x not equal to 2. So let's take a look then at our first combination. In the first part of example 4, we're asked to find h minus g of x. Well, again, this is going to be pretty straightforward. This is just going to be h of x minus g of x. And now we're not evaluating these functions anywhere. We just replace this with the functions themselves. So h of x is 1 over x minus 2. This is going to be minus g of x. And be careful here. Anytime you subtract off an entire function, use parentheses, minus all of x minus 4. So the best I can really do here is distribute the minus sign through. We can write this as 1 over x minus 2 minus x plus 4. And we could get a common denominator and try to combine all this together if we wanted to, but it's just a little bit gratuitous at this point. This works just fine. Now, as far as the domain goes, again, you have two options. Your choices are to either find the intersection of the domains of the two functions that we're working with, which are g and h in this case, look for where they overlap, or you could find the domain of the final composition, the final combination rather, before you simplify. And this distributing the minus sign through was okay because I didn't get rid of any square roots and I didn't get any x's out of denominators. So I didn't lose any restrictions with that process. So we can look at this final answer here. Either way, you're going to get the same results. If we do the intersection route, for g, the domain was all real numbers, the entire number line. For h, the domain was all real numbers except for 2. So where these overlap is all real numbers except for 2. And that makes sense by looking at our final answer here, because 2 would still cause us to divide by 0 in this combination. So the domain of h minus g would be negative infinity to positive 2 unioned with 2 to positive infinity. Now the nice thing is that if you were now asked to find h plus g or h times g, they would all have the same domain, because those first three combinations always have the same domain. It's just the overlap of the intersections individually. The only thing that potentially changes would be division, because then you would have to introduce potentially extra restrictions on top. So in part 2, let's try f divided by g of x. Well, by definition, f over g of x is just f of x over g of x. And again, we're just plugging in the functions themselves. So f of x would be square root of x. This is divided by g of x, which would be x minus 4. So that's the combination. This is the new function, f over g. Now we need to focus on the domain. And again, because there wasn't a great deal of simplification going on here, and in fact we didn't simplify at all, you can actually determine the domain just by looking at this. Or you can combine the two domains together as a starting point. So this time we're dealing with f and g. G still has a domain of all real numbers. F has a domain of 0 to infinity. So where these would overlap then is from 0 to infinity. If this were f plus g, f minus g, or f times g, this would be the domain. But because this is f divided by g, we also have to be careful to not divide by 0 now, which in this case happens when x is positive 4. So what we're going to do is we're going to take this intersection, this overlap, and we are going to remove positive 4 from the domain. That means that the domain of f divided by g is now broken up into two intervals. We've got 0 to positive 4 with parentheses because we've removed 4. And this would be unioned with 4 to positive infinity. All right, so that one's a little bit on the trickier side. But again, you can tell just by looking at this. It would be 0 to infinity because of the square root of x on top. Anything smaller than 0 would cause us to get an imaginary output, which means that's not part of the domain. But you also have to remove 4 because of the stuff down below in the denominator. This brings us then to our final combination of functions that we cover in this section, and the one combination that we spend the most time on, and this is called a composition of functions. And a composition of functions is essentially when you plug one function into another function. And so we say that the composition of the function f with the function g is denoted as, and it looks like this, f, and then you have an open circle, and then g, and this is read as f composed with g. And please do not mistake this open circle for multiplication. This is something altogether different. And it's defined by f composed with g of x is the function f evaluated at g of x. So you take the entire function g of x and you plug it into f. Right? And it's left to right. That's how you know how to read this thing. The order is very important. It's f of g of x. And this only works, of course, if g of x is in the domain of f. Because you could plug an x into g, but if the output of that g is something that wouldn't work in f, it's no good. You would get something undefined or something imaginary. You could also do this in the reverse order, again illustrating that order is important here. G composed with f of x would then be g of f of x. Read left to right. And these are two different things. F composed with G and G composed with F are not the same thing, generally speaking. So once again, let's start off by looking at an example involving discrete functions. So we've got the two functions f and g defined above, and let's evaluate some compositions. So in part A, we're asked to find g composed with f of -3. So this is, left to right, g of f of -3. And whenever you're evaluating a composition, you start on the inside and work your way out. So f of -3 is something we can handle. That's just like a problem from section 2.1. So f of -3 is 1. So what this is equal to then is g of 1. Okay? Just replacing the entire f of 3 on the inside with what it evaluates out to. But the g is still on the outside waiting for its turn. And now that it's next up in line, we just do function evaluation again. Now we have to figure out g of 1. And g of 1 would be equal to 2. All right, so it's just about evaluating the functions in order. Similar for part B. If we've got f composed with g of -3, this would be f of g of -3. So this time g goes first. G of -3. So g would take the -3 and turn it into 2. So this would be now f of 2. And now it's f's turn. F would take the 2 and evaluate it out to be 0. And so f composed with g of -3 would be 0. So once again, let's take it one step further then. We're asked to fully define the functions, g composed with f and f composed with g. So find every ordered pair for these two functions. And unfortunately, figuring out what you can plug in is not as simple as just looking for the overlap between the two this time. It doesn't work that way with compositions. Instead, with discrete functions, all you can do, so let's write this in terms of x real quick. G composed with f of x, by definition, would be g of f of x. What you do in this case is you just try everything that you know works on the inside function, f, because that will at least make it through the first step. It's not guaranteed to make it all the way through the end, but there's no point in plugging anything other than these three numbers, because only those three would make it through the very first step of the composition. So you just try everything in the inside function. So let's try it out. Let's start with g of f of -3. The first thing up on the inside function. And this one we actually evaluated on the previous slide. F of -3 would be 1. And then g of 1 would be 2. All right, so just like with the combination of functions earlier, this is going to correspond to an ordered pair, input-output. So the thing that we plugged into the composition at the very beginning was -3, and the output at the very end was 2. Let's try the other inputs. G of f of, next up for f, we've got 0. So we evaluate the f first. F of 0 would be 4. And then we evaluate the g. G of 4 would go back to 0. Input, output. So this would correspond to an ordered pair of 0, 0. We've got one more to go. We've tried -3, we've tried 0. All that's left is the 2. So we've got g of f of 2. All right, so f of 2 is going to be 0. Evaluate that first. And now we've got g of 0, but if you notice, 0 is not in the domain of g. It's not one of the available inputs. So this one hits a dead end. It's over. That one doesn't give us an output. All right, so that's it. Now that we've tried everything in the inside function, nothing else would work because nothing else would make it through the very first step. We've got our answer. We can fully define our function. G composed with f has two ordered pairs. We've got -3, 2, and we've got 0, 0. If you are asked to find the domain, this is one that's really tricky to find the domain up front. Instead, what I recommend is doing this to define the function and then determine the domain from the function you defined. So the domain of this composition would just be -3 and 0, the inputs that made it all the way through. All right, so now that you've seen an example, try pausing the video here and see if you can fully define f composed with g. All right, so this time f composed with g would be f of g of x. So g is the inside function this time around. So the inputs for g are the thing I try. So I need to plug in a -3, a 1, a 2, and a 4. So let's just try it out. We'll begin with f of g of -3, and this one we worked out on the previous slide. G of -3 is 2, and then f of 2 would be 0. So that's an input-output. Next up in g, we've got the 1. So g of 1 would be 2, and then f of 2 would be 0. So that's going to be an input and output. Next up, we've got f of g of 2. G of 2 is 6, and then f of 6 doesn't exist. 6 is not one of the available inputs for f. So that one we throw out. And then we've got one more to go. I'll do that one at the top of the screen. So we've got f of g of 4. G of 4 would be 0. And then f of 0 would be 4. So that one did work. So we had 3 that worked in total. F composed with g, the function, has 3 ordered pairs. From the first one, we've got an input of -3 and an output of 0. From the second one, we've got an input of 1 and an output of 0. And for the third one, we got an input of 4 and an output of 4. Once again, if you were asked to find the domain of this, now it would just be the set of first coordinates, x values. So the domain of this composition would be -3, 1, 4. So now let's look at some compositions with continuous functions. And we're going to use this example to illustrate an important point about domain. So in example 7, we're given f of x is equal to square root of x, and g of x is equal to x squared. And to begin with, in part A, we're asked to find f of g of 2. So once again, you just evaluate from the inside out. So I'm going to start with the g of 2. Well, that just means we plug 2 into g. So this would be 2 squared, or 4. And then we evaluate f of 4. Since f is square root of x, this would be square root of 4, which would give us 2. Next up, we've got g of f of negative 2. All right, so once again, just start on the inside, work your way out. So we start with f of negative 2, which would be square root of negative 2. Well, that's a problem because we're working with functions here, not just trying to solve equations, which means we don't want imaginary numbers. This is no real output. So in other words, we would say that negative 2 is not in the domain of this composition because it does not give us a real number output. It doesn't make it through the first step. For part C, we're keeping it more abstract again. We're finding the function g of f of x. So this time, I'm just going to replace f of x with what it's equal to, square root of x. And now I'm going to plug that whole function into g. And since g is x squared, I'm going to replace that x with square root of x. But square root of x squared is equal to x. So this would be, if I wrote this in a more compact form, g of f of x is just equal to x. And so what you do by keeping it in terms of x like this is you create a shortcut rule from going to the beginning of the composition to the end of the composition. So now if I wanted to find g of f of 2, I could just plug that into this shortcut rule and it would be equal to 2. G of f of x is just equal to x. The problem is that comes with some limitations. So last but not least, in part D, we're asked to use this shortcut rule that we just created to find g of f of negative 2. So if we just plug negative 2 into this shortcut rule, the question then is, does g of f of negative 2 equal to negative 2? Just plug negative 2 in for the x's. Well, it certainly looks like it works from the shortcut. And in fact, if you are asked to find the domain of this function x, you would probably say all real numbers, but unfortunately that's not the case. Because if you go back up to part B, we said that g of f of negative 2, when we did it one step at a time, had no real output. Because you have to plug the negative 2 into f first. That's the definition of the composition. And this is actually the real answer. And so the problem is, when we went from this step to this step, if you look at the composition here, square root of x squared, you can tell that if you plugged in negative 2, the square root would give us something imaginary. That's not a good thing. But once we squared away the square root, we lost that. And so we're going to use this to jump into the idea of talking about domain now, and the fact that simplifying the composition causes you to lose restrictions. So you've got two ways to find the domain of a continuous function, two different approaches that will give you the same result. And both of these stem from the fact that you can't necessarily look at the simplified final answer and tell what the domain is. You might have simplified away restrictions. So your two options then are you can do an intersection, although it's not just the intersection of f and g anymore, like it was with the basic combinations, addition, subtraction, multiplication, and division for the most part. Instead, your options are to either do an intersection of the domain of the simplified composition, f of g, but then you intersect that with the domain of the inside function, g. What this has the effect of doing, by intersecting it with the domain of the inside function, is you're basically adding the restrictions that you simplify away back in. All right, this makes sure you pick back up any restrictions from the inside function. And although this is written in terms of domain of g right now, if you were to swap the order of this, the names would also swap. So a good way to think of this is instead of domain of G, you intersect it with the domain of the inside function. Sometimes this is the easiest approach if the composition itself, before you simplify, is super messy, but after you simplify is quite nice. Then breaking it up into two parts, the simplified composition and the inside function, might be the most effective way of finding the domain. Having said that, the other way is a little bit simpler. And it's the same that we talked about back with the basic combinations. You can determine the domain of the composition from the composition itself. You just have to make sure you do it before you simplify. So in the example on the previous slide, I would have looked for the domain before I got rid of the square root symbol, right? Because at this point, I can still tell that I don't want to plug any negative numbers into the square root. And this will be the approach that I generally use, because here in Math 101, we don't really use functions that get so messy that the unsimplified composition is very difficult to work with most of the time. So let's try it out. Let's find some compositions of continuous functions and their domains. So we're given four functions to work with in this case. We've got an f of x, which is x minus 2. G of x is square root of x. H of x is 1 over x. And r of x is x squared plus 2. In part A, and for all of these, find an equation defining the function, that shortcut rule, and state the domain of each. So we're going to begin with g composed with f of x, which by definition is g of f of x. All right, so again, I'm just going to replace f of x with what it's equal to, x minus 2. And then now this just becomes function evaluation. I'm evaluating g at x minus 2. So g of x is square root of x, but now I'm going to replace that x in the square root with x minus 2. Right, again, this is basically us plugging f of x into the function g. So this is our equation defining the composition. This doesn't simplify at all, so this is as good as it gets. And because there's no simplification taking place, we can determine the domain from this final answer. And so, like always, when dealing with square root functions, we need the radicand, the inside of the square root, to be greater than or equal to 0, which in this case means x needs to be greater than or equal to 2. So the domain would be 2 with brackets to positive infinity. Next up, we've got part B, h composed with f of x, h of f of x. Once again, the f of x on the inside is x minus 2, but this time we're plugging it into the function h. So this would be, instead of 1 over x, 1 over x minus 2. And again, this is just us plugging the function f of x in for x in the function h. All right, and once again, that's it. There's no simplification to be done here. That's as good as it gets. And because there's no simplification, once again, we can find the domain from this. This is a rational function. We don't want to divide by 0, which would happen if x were positive 2. And so the domain would be all real numbers except for 2. Negative infinity to 2, unioned with 2 to positive infinity. Let's take a look at 2 more. So in part C, we've got h composed with r of x, h of r of x. R of x is x squared plus 2, so now we're going to take that and plug it into h. And so if we plug that in, we get 1 over x squared plus 2. Again, no simplification to be done for this one. This time around, if you look for the domain, this is again a rational function, but this is something we run into every now and then. If you take this denominator x squared plus 2 and you set it equal to 0 to try to solve it like an equation, you would get square roots of negative numbers, imaginary x's. There's no real solution to this equation. And the reason for that is because, think about it, x squared as a number by itself, no matter what you plug in for x, will always either be 0 or positive. You can't get something negative when you square it. So if you take something that as its smallest is 0, and then you add 2 on top of that, no matter what, this denominator is positive. There's no real number x you could plug in that would make this denominator 0. So even though there's an x in the denominator, no actual value of x could cause you to divide by 0. So the domain of this is actually all real numbers. No restrictions necessary. Next up, we've got R composed with G of x. So this is R of G of x. G of x is square root of x, so we're going to take that and plug it in to the function R. And so this would now be the square root of x squared plus 2. This one does simplify to x plus 2. But this is just like the previous example we saw in 7, where we were leading up to the idea of talking about the domain. If you just look at the final product, you might say the domain is all real numbers. That's not the case. Look before you simplify. Because the inside function is square root of x again, we can only plug in x is greater than or equal to 0. So even though the final simplified function is x plus 2, the domain is only 0 to infinity. Let's take a look at a few more examples of compositions just for a little bit of extra practice. So we've got some new functions this time around. F of x is 3x minus 1. G of x is x squared plus 1. And h of x is x plus 1 over 3. So try pausing the video now and see if you can evaluate parts A and B of example 9. All right, well, again, you evaluate from the inside out. So this is g of f of negative 1. Let's start by figuring out what f of negative 1 is. So we plug that in. 3 times negative 1 minus 1. That would be a negative 3 minus 1, or a negative 4. So this is going to be g of negative 4. Now we evaluate the outside function. Plug negative 4 in. Careful with parentheses. Replace x with parentheses. Negative sign and all goes inside. So we get negative 4 quantity squared plus 1, which would give us a positive 16 plus 1. So our final answer here would be 17. For part B, h of f of w. So f of w would be 3w minus 1. And then we plug that in to the function h. So this would be 3w minus 1, but then you still have the plus 1 divided by 3. All of this just replace the x in the top left corner. Well, in this case, the -1 and the +1 cancel each other out. There's no exponents or multiplication, so that you can just drop the parentheses. And this gives us 3w over 3, which reduces to just w. Let's take a look at some of the other things you can do with compositions. So it's not necessarily just 2 functions that can be composed. You can compose 3 functions or more than that at a time. So in part C, we're asked to evaluate h composed with f composed with g of 3. And again, it's just an extra layer. You read from left to right. So this would be h of f of g of 3. And you just start on the inside and work your way out. So we'll begin with the g of 3. We plug that in, we would have 3 squared or 9 plus 1. So that would give us 10. So this then would be h of f of 10. We replace the g of 3 with the 10. Next step. F is next in line, so now we evaluate f of 10. So if we plug that in, we would have 3 times 10, which is 30, minus 1, which would give us 29. So this is now h of 29. And now last but not least, we can evaluate the function that is most on the outside, h. And if we plug 29 into h, we would have 29 plus 1 divided by 3, 30 divided by 3, which would give us 10. All right, so you read left to right to set up the notation, and then when you evaluate, you work your way from the inside out. On top of that, you can even compose a function with itself. So let's say we had f composed with f of x. Well, by definition, this would be f of x. The f of x on the inside would be 3x minus 1. And now we're going to take that 3x minus 1 on the inside and plug it into f again. So this x here, we're going to have 3 times, and I'm going to replace that x with parentheses, 3x minus 1, and then we still got the minus 1 on the outside. So I need to distribute that through, which would give me 9x minus 3 minus 1, or 9x minus 4. So let's take a look at one more example, and this one's pretty straightforward, but it illustrates the fact that sometimes we use compositions without necessarily thinking of them as compositions. So in this case, we have y defined in terms of t, so we know y is equal to 3t squared minus 3, and we know t in terms of x. T is equal to x minus 1. We're asked to use this information to write y as a function of x. So we don't want y in terms of t anymore. We want y in terms of x. So what we do in this case is a substitution. This t we know is equal to x minus 1. So I can swap that out. Y would be equal to 3. I'm going to replace the t with parentheses, just like with function evaluation. And inside that parentheses, I'm going to swap that out with x minus 1. So this is a substitution, but this is a composition. That's exactly what this is. We are composing these two functions together. And from here on out, it's just simplification. So we need to start with the x minus 1 squared. If we FOIL that out, That would give us x squared minus 2x plus 1. But it's still going to be that 3 out front times all of this. So that's going to give us 3x squared minus 6x plus 3 minus 3. And so our final answer here, y in terms of x, y would be equal to 3x squared minus 6x. And that's it for section 2.4, operations with functions. Now there's a lot of variety in this section, but to be honest, the types of problems here makes it seem a lot more complicated than it actually is. First off, given discrete or continuous functions, be able to evaluate a sum, difference, product, or quotient. And again, make sure you know the language. Sum is addition, difference is subtraction, product is multiplication, quotient is division. So it's saying be able to perform those 4 base operations with discrete or continuous functions. On top of that, the second problem type, you should be able to fully define a sum, difference, product, or quotient. So this is basically examples 1, 2, and 3. Right? The third problem type is the same as the second, but with continuous functions instead of discrete. So given continuous functions, be able to find and simplify a sum, difference, product, quotient, and state the domain. And remember, the domain is the intersection of f and g, if that's what you're combining together, or you can find the domain from the unsimplified combination. And then numbers 4 and 5 relate to our fifth way of combining functions together, compositions. Given discrete functions, be able to evaluate and fully define a composition. And given continuous functions, be able to evaluate a composition, find an equation representing a composition, and then the trickiest part, state the domain. All right. As always, you guys can find examples of these problem types on the study guide for the exam. If you have any questions about the material, please make sure you let me know, and I will see you in the next video.